Okay. Share the screen. Okay, and then we're gonna start the Conda environment list. Conda activate. I-37 ITS 520 section 1. Okay. All right. So like I said, we're going to do a review of where we were. So I'm going to start the Jupyter notebook. And then it should be fun for you guys, I would think, to try to solve this. As this is, like what you should be doing, right? So solving, this is machine learning. But, it's not about pressing a button and it works. In fact, almost never works in the first trial. And then you have to kind of like, so I think this would be a good exercise. Let's not sure what it's doing there. Okay, so anyway, it seems like it's good. All right, so let's start this one. This is the data set is here, wine quality. So it should be this Jupyter. And we're gonna kind of review where we are. All right, so I'm gonna do the kernel, clear the output, okay? So the goal is to build a model, the best possible model that we can build. And whenever you're building any kind of AI, whether it's this wine quality thing or ChatGPT, right? Whatever it is, we need some metric. That's how we will know. It's like we have a model and the model will need to have a learning objective. And then given that learning objective, it will predict. And we want to compare those predictions to some kind of something that we can measure performance, right? And then based on that performance, we can direct to see if the model is doing well or not. And so this will be basically our exercise here to see how well this model is doing, okay? So I've cleared the output. So I'm gonna take a look at it. Yeah, so it's missing. Right now, I think all we've been able to do is we built a linear regression. So today we will be building all the architectures that are important, like neural networks, even a deep learning architecture, just not any advanced deep learning algorithm. But we will be doing a deep learning neural net, okay? And we'll be just exploring some techniques. So the first thing probably that I want to do is just to have some metric of performance, okay? And the metric of performance is something called the R-squared, okay? So there are many metrics for many problems. Like if you're translating from some language like English to Japanese or something like that, you use a metric called a blue score, right? So any problem, multiple problems will have multiple metrics, right? Or individual problems will have individual metrics. For classification problems, we will see that we will use something called accuracy, precision, recall, and the F measure. And we will explore those when we get to those, right? But currently, we are not doing classification problems. We are doing regression problems, right? And that is when we're trying to predict real valued numbers. Like we're trying to predict the price of a house or a car. So it's like, $25,000 and 25,501, something like that. Or the temperature that we were doing, we were predicting that is 98 degrees or 68 degrees and so on. So that's called a regression problem. And for that problem, we have basically two metrics in general. One is the error, right? And that's not as meaningful, but we do have one that's really important called the R-squared, okay? And it stands for the coefficient of determination. So that's the metric that we will use to measure the performance of our model. And then once we have that metric, all we will do is try to improve that performance. You see that and so we will try everything that we can to make our model better and better and better. And you guys will see the performance. So I did this with the other class, and I think we were able to get to 0.3 R-squared. So what does that mean? So the R-squared is basically a measure that you want to go to 1. Okay, 1 is like perfection. Okay, so that's like if one of you guys you get 0.98 0.98 R square, I want to know how you did it. You know, this is basically, I'm going to study your model and everything, right? And that's the competition. The other way of looking at it is, you know, whoever gets 0.98 gets an A or gets $1 million or whatever, right? So wins the contest. So it's really, this is how machine learning works. It's all about some metric, and whoever gets the highest score is, you know, does great. If you think of the very famous competition in 2012, everyone was getting around 0.72, and then University of Toronto entered the competition and got a 0.82 using something called deep learning back in 2012. And that's like, it revolutionized AI, right? And it was just a 0.10 difference, but that made a huge impact. Okay, so that's kind of what, you know, you're basically replicating the way that machine learning works. So that's what we're gonna do. So I'll just do a quick review of the code so I know where we are, and then we're gonna start trying to think about how to get the precision, and then, or sorry, the performance metric. And then after that, we're just gonna throw things at it to try to improve performance. Make sense? All right, so when we did this last week, okay, we basically added the libraries. So we will be adding a new library today for the R square. So let's add that in. So I'm gonna do from sklearn dot metrics. I'm going to import R square score. So that's the name of the function. Why sklearn? As I said before, sklearn is used by a lot of people. I like it. Do other frameworks have an R square? Probably. Okay, and you know, it just depends. If we use sklearn after performance, we may need to detach the tensor from the graph, make it into a NumPy, and then run it, right? So we've talked about that before. All right, so the libraries for today, NumPy, Torch, of course, Pandas, sklearn, random is there. We have torchnn, functional, Optim, so we've done those, matplotlib, okay. And then the heat map is there, yeah. Train test split we've already done, and we've already done tensor dataset and tensor data load. So really there should only be one library that we are adding. So let's go ahead and run our code, make sure that it does work. Move this a little bit. Okay. Okay, so it's taking a while. All right, there we go. Hit. Now let's run the other ones. And we've added all of our libraries. The next set of things that we're gonna have are the batch size, which we set as 16. The learning rate, which for this problem, you may need to play with the learning rate, right? So I'm gonna write in for you to try other learning rates, not right now, but when as you're doing the homework assignment, right? You can play with multiple learning rates. So you can do 0.001. You can do 0.030 and a 1. You can try 0.003. You can try, and then also with fewer zeros, 0.01, 0.03. So there's no real, you know, there are some algorithms that when you run them, they kind of suggest a learning rate to use, but otherwise you can just experiment and get a feel for what's going on. Okay, so we're just going to leave it at 0.001 for now, and the number of epochs. Since we're going to be running this several times today, maybe we need to like, so it doesn't take too long. We are going to reduce the number of epochs to 400 just so that we can be a little bit more faster. Now, another thing that I'm going to add is a little variable called epsilon. So epsilon equals 0.0001, and that variable is, you'll see later, we're going to use it for the normalization or standardization. It's just like a convenient number that we're going to use to prevent, basically like a division by zero error. Okay, so we're going to be using that. All right, so let's go ahead and run this one. All right, then we're going to check the data just to make sure everything is in good shape. So we are reading our data, wine quality, all right? And we're reading it as a pandas data frame. So we can go ahead and do that. Nothing changes there. We can print it and take a look at it. Notice, very important right now, that the values are not in the same ranges, right? So this goes in a range from 0 to 7, maybe. These are decimals here. These are not. These are actually larger numbers like 111, 110. So they are in different ranges. And in general, whenever we do machine learning, we want all the variables to be in similar ranges, like from -1 to +1 or from 0 to 1 at least. Usually if it's from 0 to 1, it's called normalization. If it's from -1 to +1, it's called standardization. And they're just basic equations that we can compute, and we will. All right, so that's basically something that I want you to pay attention to right now. This is really important for I'm not going to show the proof, but in general, machine learning really likes normalized numbers, okay? So, and we'll actually see this. So if we know that the performance is the R-square metric, and we know that the higher it is, closer to 1 it is, the better, then we're able to see the effect of not having standardization and having it, right? And so that's one of the things that we will test today. So obviously right now we don't have any kind of normalization or scaling. So the performance will be something, and then we'll see what happens when we actually add this scaling computation, basically. So let's go ahead. Now let's print the list of the names of the headers. So we had 2. I already showed that exercise, so I'm not going to repeat it. Okay, and then we can, we talked about correlation coefficient, so that also does not change. So today, our focus is mainly on the model. All right, then to process the data, I believe we had already covered that in a lot of detail. So the first thing we did was convert our pandas data frame into a NumPy array, and there it is, so that's done. Then we printed out the shape just to kind of remind ourselves. So remember, there's about 5,000 samples and 12 columns. The last one is the value that we are trying to predict. And we're going to do a split where we have about 4,000 for training. All right, so this is the part where you slice, right? The variables that you want, so the X and the Y. So we've already covered that, and you can see there's the slicing basically. We can look at the data. Now, this data is only values 1, 2, 3, right? It's the quality score given. And this might be presenting a challenge to our model. So like I said, the goal is to get really good performance, okay? And so really if, we need to predict if it's a 7, that it is a 7. That's what our model needs to predict. All right, so remember that we're using, what is it? Oh, I haven't done the split, I guess. All right, so let's do the split, and then we'll see what the numbers are. So let's print out. This is the random seed, so we've talked about that. There's the split, and now we can look at the shape. So remember, every time we run this, we're going to be using about 4,000 samples for training, and we're going to be using about 908 samples for testing, right? And the R-square is going to be on the 980 test samples. All right, so we could calculate an R-square on the training set. I mean, that's something that sometimes is useful also. But really, the real measure of success is to see how the model performs on the test set because it hasn't seen that data before. Okay, so we're going to take a look at that. We do the data type correction from float 64 to float 32. Just in case we get an error, and then we finally convert these into torch tensors. Okay, so if you look, there's the normalization section that I left before, and I did talk about how we have the 2 methods. Today, I will be showing the standardization approach. Okay, so we will take a look at that. In general, I've read the literature, not all the literature, but most of the literature that I've read, let's say, usually recommends standardization. So that's kind of what I have a tendency to use. You guys can try normalization. Maybe you'll get good results. Okay. So we'll talk about how that works in a second. And basically do that. But before I do that, I want to calculate the performance metric of R squared. Okay. So we're going to do that. So we'll come back to this part here. Then we've done the create data loader part. So if you remember, we take X train and Y train tensors. We load them into a tensor data set. And then train DS gets loaded into a data loader. We decided that the batch size is of 16, and we shuffle our data. Okay, so we've talked about all of this already. All right. So we built one architecture, correct? Pretty sure we've done one of these. Yeah, so I have it, I guess. Let me move this. I want to have it a little bit like I have it for the other class. So I'm going to just say here, neural network architectures. So this part is what we're going to focus on today a lot, okay? Because we're going to build like 4 architectures. We only had one from last week, but this is really important. So I'll review this one. Oops, not that. I'm going to move the linear regression to the top here. Okay. All right. So if you remember, this is an important thing for you to like understand, right? This is like one of the most important things. This is how we can build our inference function, right? So this is the y equal wx plus b, right? That we did for the temperature generation or calculation, okay? This is like a good approach. Most people take this approach to build the algorithms, and as much as possible this semester, I will try to take this approach to build our inference functions to be consistent. And as you will see today, they just get more complex. Okay, so we'll talk a little bit about that. So basically what we're doing is class inheritance. So as you can see, we can define our own class like linregnet, and then we provide as a parameter nn.module, which is the provided PyTorch general neural network class, right, to build our inference function. So we inherit that. This expects to have 2 functions, the init function and the forward function, right? So we've talked about that. And then we just, in the init function, we initialize everything. So we initialize the superclass, and then we basically define our variables that will define our architecture, okay? So that's the key thing. And if you remember, we've only done a linear regression where we have 11 inputs and 1 output. And we went over that network. We drew that, right? So today we'll be doing more complex things, and I will kind of draw the diagram of what this is supposed to look like. All right, so that's the init function. Then we have the forward function, which is where we actually build the network. So the idea is given X, what is Y, right? But obviously this can have a lot of things going on. So we'll play with them, and I'll throw stuff at this because our goal is to improve performance, right? So that's linear here, takes an X, and then basically all it does is it's like mapping our input vectors are of size 11, right, each one, and then batches of 16 by 11, and then we predict 1 value, right, which is this quality score, and then we return that. All right, so obviously we'll be creating more classes for this one, so we'll come back. We'll do multi-layer perceptron, deep learning with 2 hidden layers, and then something else that I'm going to give you. All right, so now let's take a look at the training loop. So just to make sure that the beauty of this approach is that, we can replace the initialization of linregnet with, multi-layer perceptron, deep learning, just easily by changing the instantiation that we're doing. All right, so let's take a look at train loop here. basically we have, it takes number of epochs, the model, loss FN, and opt. All right, that's the training loop function. We're using the two for loops because we have 4 epoch in range of n epochs. So this is, remember, we are, every epoch we give it all the data, right? But every time we give it all the data, we're reading in batches and shuffling the data, and that's really important. We use train DL, which is our data loader, right? XB and YB. So XB goes into model, we predict. YPred and YB get compared in loss FN, and that's basically the loss. Then we do the zero grad, right? So we've talked about this, loss backward and up step. So you know that this is where you're actually calculating the gradients and then modifying the weights. All right, and then finally, we're gonna print out the loss, right? And all of that is the same. And this is what we're gonna be using to train our model. So nothing changes there. All right, and then over here, down here is where we invoke everything and bring it together. So let's take a look at that. So we instantiate. Currently, we only have one architecture, which is the LinRegNet. Okay. And then given the model, we initialize also the optimizer, which you can see as Atom. We've talked about this. These are the parameters, the learning rate. We initialize the loss function, and then we just call train loop. Okay, before we hit run though, now let's start thinking about the new code that we're gonna add. Okay, so now that's the review. Okay, I don't want to run it yet because that's the only cell I haven't run, because I want to add in the new code. All right, so now down here, I'm going to create a new cell. So if you notice, what I'm doing is first I train the model on the trained data, like about 4,000 samples, right? And once I've trained the model, remember I have a test set of about 980 samples. And on that, I'm going to measure performance, okay? So that's really what I'm going to do. I'm going to do a couple of things here. Okay, so the first thing is I'm going to write evaluate model here. Evaluate model. Okay. We already have the R-square that we're going to be using. And now I'm going to basically create a variable YPred test. Okay, so this is the predicted for all the test data. And I'm just going to invoke the model. The beauty of our model is it's meant to take batches of any size. So we could give it 1 sample and it's going to predict. We could give it 16 samples and it's going to predict, or in this case, we're going to give it 980 samples, right, in the test set, and it's going to predict the value for each one. Got it? So let's go ahead and give it X test TR, right? So if we look, that should be the name of our variable. Yeah, X test TR, and then Y test TR is the corresponding values that we want to compare to. Okay, so that's the first thing. Let's not run it because we don't have a trained model yet. We're just writing the code. We want to print out the shape. So let's do YPred test dot shape. Okay, and then once we do that, we're going to actually print out the score, the R-square, okay, on this test set. And this is the thing that is going to say who has the best model. So let's go ahead and do print. And then we can say testing R-squared, or coefficient of determination. Okay, R-squared, usually write it like that. Do something like that, and then comma, and then we're gonna print out in here R-square score. Okay, now this R-square score takes 2 things. It will take the predicted and the real data, right? So Y test underscore TR is the torch tensor. Y test. Oh, actually, Y test TR is the real data, right? Is that the name of the real data? Yeah. y test tr. So this is the real data. Remember, if you give it x test tr, which we did, then the corresponding vector should be y test tr. So that's the the variable, but I'm going to convert it to numpy. Okay, because this is sklearn, not PyTorch. Does that make sense? All right, and then that vector will be compared to y test spread, which is this variable over here, okay? Y test spread. Oh, I'm sorry, yeah, sorry. Y spread test. And this one, you can play with this. I usually let it error out, right? And then that way we understand why we're doing what we're doing. So let's just do numpy right now. Y test spread, like that. You know, it's good thing sometimes to let things error out and see what the error is so that we actually know exactly what's going on. All right, so now we have our R squared. That's, you know, really important. If I'm building a competition with you guys, like I said, this is really important, right? So now we have everything. So let's go ahead and train our model because we can't run R squared without it. So I believe we ran the architecture. Okay. Okay, so that's the function. There we go. And I only did 400 iterations, and that's intentional to, so that's in. Okay, that's intentional so that we can run this quickly. Obviously, you guys, you know, can go home and run it overnight, right? And maybe that could be the solution. I don't know, honestly. Like, I haven't looked at this. I intentionally have not looked at what the best performance will be for this. And I'm hoping you guys will do a great job. All right. What I do in these classes actually is I print the PNW lion, like 3D print, and whoever gets the best score gets it. So that's, I might give you that. All right, so do a good job, okay? So as you can see here, the loss, remember, don't, like the other class got confused thinking because the loss needs to go down, that the R squared needs to go down, but it's the opposite, right? So you just understand how the metrics work. So here we want the loss to go down, of course, but really we want the R squared to go up, okay? So those are the metrics. So here we can see it kind of, yeah, it kind of it's getting stuck there in those values. And our goal basically is to improve results. However, when we do this, we don't really know exactly, right? Because it's fluctuating a lot. So we need the other metric, R squared, which should be better. So let's give it a minute. And let's wait for it to reach 400. And then we can compare the R squared, okay? Any questions meanwhile? Does this make sense? Okay. While it's running, we can add a little bit more code. So a couple of like things that are useful. I always like to look at the shapes, as you guys know. So I'm going to do y pred test dot shape. Just don't run it until you fit. Huh? I had it already. Okay. Y pred test. Okay. All right, you're right. Where is it at? 280. All right, so while it's doing that, then another thing that I would recommend that we do is printing out the actual values. I like to do that sometimes. Like I literally like to print the real values and the predicted values next to them and kind of look at them. Although here the problem we have is that there are 980 test samples. Imagine if you had 10,000 test samples, that's even more, right? And that's a lot to read through. So what I'm going to show you after that is a little graph, a nice little visualization tool that allows you to kind of see everything like in one image, if you will. So we'll build that one as well. Yes. So let's see, where is it at? It's almost done. So let's wait for it, and then we're going to start predicting. 380. So that should be the last one. I think it, yeah, it kind of gets stuck at 0.41, but we would really want this to be like 0.001 or something, right? Okay, so it finished. So now we can go ahead, let's save it, click run. And now we're going to predict, right? We use the model, and as you can see, okay. Oh, lowercase, right? Is that what it is? Okay, let's try it again. Okay, so it predicted. So now I'm going to print a shape, and as expected, it should be 980 and 1. Do you guys see that? Now comes the moment of truth. This is something when you do machine learning. Imagine you spend 3 months collecting data, month or two thinking about your model. Finally, you get to this point to look at the performance, and you're like crossing your finger. Oh, okay. Oh, yeah. I intentionally left this error. Read the error. What does it say? Huh? Do you see the error? Can't call NumPy on tensor that requires grad. It's telling you that it's still attached to the computational graph. So it's actually suggesting what you should do. Take the tensor, detach it, and then do NumPy. Do you guys see that? I intentionally did that so that you would understand why you need detach. Okay, it's a PyTorch thing. It's literally how it works. So now let's go ahead and do it again. Run. Next to detach, I need the parentheses. Oh, yeah. Very good catch. Thank you. All right. So try another time. There it is. And then you get here and womp, womp. You get that 0.25, right? That's not good, unfortunately. So that's your homework. Literally is make that a 0.85 or so somehow. All right, so we're going to throw a lot of things at this problem and see how we can get it to be better. At least, take it to the limits. Let's see what, we're going to hit this problem really hard. So there's another tool that I have called XGBoost. So it's not a neural network one. It's a regression tree thing. And we're also going to use Weka, which is a tool that has a whole bunch of regression models. So we're going to throw everything that we've got at this problem eventually, but after you guys do the homework with neural nets, okay? So I just want to see how you guys attempt to solve it, and given the things that I'm going to give you. Does that make sense? Questions? All right, so I'm not hearing any questions. So let's go ahead now. So you can see it's 0.2589. This is actually what I posted on the GitHub. So what can we do? Before we start trying to improve things, let's get more information, right, of what's going on in the results. So one thing I'm going to do is print the results, okay? And then after I print them, I'm going to try to visualize them in a nicer way, okay? And then from there, you guys can start adding stuff to improve results if you can, okay? So what I was going to do next is I like to print out the actual results. So let's just I'm going to hit save, hit run again. Okay, and now literally just use the model and predict one by one and print it out, and print it with the real value. So we're not going to predict, actually. We're just going to print. We already have it. So I'm going to do 4i in range. Okay, conveniently know the size. So I'm going to do like len of x test tr. So that's I can hard code the 980, but it's bad practice to hard code things. So x test tr. Okay. All right. And now let's go ahead and print some stuff. So I'm going to do print. Okay. And this is just so I can separate out the results. basically. And now let's do, I'm gonna print a little like data of what I'm looking at. So I'm gonna, oops, sorry. I'm gonna say pred and real. And really, I just want to print them side by side. So I'm gonna make them into NumPy variables. So I'm gonna say NP real. And so I'm gonna take Y test TR, which is the real data, right? And I'm going to index them, as you guys know how to index. I'm just gonna say I, and then this is a tensor, torch tensor, right? So I'm gonna do detach, why not? And then I'm gonna do NumPy. Okay, I just want it to be NumPy. I'm gonna repeat the same NP pred pretty much very consistently. I'm gonna do Y pred test, Y pred test. Okay, I'm gonna index it. I'm gonna align them. Okay, and then this is also a torch tensor, so I'm gonna detach it, and then I'm gonna make it into a NumPy array, just like that. Okay, guys, and that's the idea, is so that I can print them out together. So I'm gonna do print here. I'm gonna, I like printing tuples, so let's just do that. So I'm gonna do NP pred is first, comma, and then NP underscore real. Now, before this should work, and this should print out our results. And actually, we can do it. So let's go ahead and do that. So there they are. So now you could do the analysis. Now they're still in NumPy array form. So what we could probably do is just put in 0 here. And like that, so that we index out just the values. So go ahead and try that one. Yeah, and now we've got the value. And as you can see, the numbers in the real data don't have a decimal. They're like 6.0, 5.0, 3.0, and so on, whereas the model is predicting 5.701. Now, you could argue that the machine learning algorithm itself could learn to predict that it needs 5.0, 5, 6.0. I mean, the machinery is there for it to learn that, right? With enough data, it should get more precise. However, this is a quality, a rating kind of a problem, not exactly regression, right? A little bit more like rating. So there's something to think about there. So I'm throwing a hint at you to look at that as you're working through this problem, right? But so far, they're kind of close. They're just not perfect with the R-square, right? So we did that. However, you'd have to look at all of this, right? That's a lot of, imagine if it's, as I said, if it's like 100,000 test samples, that's a lot of data to look at. So maybe you want to visualize it in another way. So that's what we're going to do. We're going to create a visualization tool. So for that visualization tool to work, we need to have two lists, right? The two lists are going to have the same size, and one is going to be called list underscore preds. A lot of things can be done like this for visualization. So list preds, and then we're going to do list underscore reals. Okay, just like that. Make sense? And now down here, we're just, as you might imagine, we're just going to append these values in there. Okay, so we're going to do list preds, list underscore preds dot append. And we're going to append to it. So for preds, we're going to append NP pred 0, right? And for the other one, list reals, we're going to do, append. And we're going to append to it NP real. square bracket 0. Just align it for better presentation. All right, so we have that there, right? And that should give us our data. So let's go ahead. That should be enough for our data. So let's run it. Still the same results, but now we have our list. Let's make sure we don't have any errors or anything like that. Okay, so no errors. Great. Let's save it. So now what we need to do is we need to print this out as a plot. So that means we're going to use matplotlib. Okay, and you guys, I recommend there's a visualization class going on, I think. So I don't know if you guys or will be going on. So take it if where you will learn more of these techniques. So my focus is not on that. All right, so let's go ahead and do that. So we are going to build that function. So just give me a second here. All right, so okay, so this should be, yeah, so we just need, I think we already had PLT right at the top from matplotlib. So if I remember correctly, we just call PLT dot figure. And then we can specify figure size. So fig size equal. And you can change this, but I'm just going to try like 13,4. All right, then we should invoke PLT dot plot, and PLT dot plot will print out the results basically into a figure. All right, so let's do the first one is what? What were the names? List preds and list reals, right? So let's do list reals first. List reals, right? Okay, that's what we're gonna plot. Does that make sense, guys? Okay, and then we specify label. This is just so that we can know what every color is. So I'm gonna do label equal real. Okay. Oops, sorry. And then we can also specify a color. So this should be red, R. Okay. Then I'm going to do another one, the other data. So that's going to be PLT dot plot. And that's going to be, what is it? List preds, right? And the label for this one should be pred. And let's just, this should be just one equal. I don't know why I wrote. So label, this is real. Okay, and that should be enough, but we're going to add a few other things to this just to have it be more presentable. So let's go ahead and run this one. And what do you guys think? You should get that figure, by the way. So what is that figure doing? How would you interpret that figure? What's the x-axis? Goes from 0 to like 1,000, right? So what is it? The what? The samples. Yeah, very good. The 980 samples, right? And on the y-axis is basically the R-square values, right? So what this then tells us is we're comparing the predicted to the real. So if we had a perfect model, What would you expect to see? All blue, very good. Exactly, very good. Good job. You can see that the blue, the model seems to be almost at an average, right? Prediction, whereas the red is a little bit like in an outer range. So this is yet another metric that you can just use to really quickly see how your model is performing. Got it? Does that make sense? Now for completion, let's just add, let's make this graph a little bit more presentable. So we're going to add a title, for instance, and the X label and the Y label. Okay. Now the values, did I say from 0 to 1? I was thinking of the R square. Sorry, I meant it should go from 0 to 10, right? Yes? On the Y-axis? Yeah, go ahead.
The second one, should that label be right?
Oh, yeah. Sorry. They should be pred. Yeah. Very good. You're right. Thank you. Doesn't change anything, but because that's really just for like presentation, but yeah. Now I think I said that the y-axis should go from 0 to 1. That's not correct, right? I was thinking of the R square. Instead, it should go what? What should be the range there? 0 to 10. Very good. Yes, because it's what we're predicting, right? It's exactly what's here. These values over here, right? So, and they're the ratings, which go from 0 to 10. So as you can see, the real data seems to be, there's a few 10s and a few low values in there, but a lot of the things that our model is predicting seem to be averaging. So it's like an averaging model that we have, right? I mean, I could, just by looking at this, if somebody told me make a model and I don't know anything, but I look at this, I'm sure 6, right? That's it. Made a model 6, right? Because if you notice, it's like an averaging model at around 6. You guys see that? And so a lot of models actually, like a regression tree, for instance, when it builds the first node, guess what it predicts? You know, just the average. So it predicts 6. And then after that, it starts adding things to make it more precise. Okay. So anyway, our model seems to be just averaging basically, not exactly, but so this tells us something else. Okay. All right. Very good. So let's add a few additional things to our graph because these graphs are really great. You can actually click plt.save and say something like DPI equal to 300, and then you have a very presentable graph that you can add to your document, your research paper, your whatever you want, you know, and be exactly what you need. Okay, so very, very useful. All right, so let's build a graph with a little bit more details. So I'm going to add a title. So I'm going to say plt.title. And in the title, I'm going to say, what do we call this? Preds versus real, maybe? So this is a plot of Preds versus real. This is a great graph in regression, I would think. There it is, Preds versus real. What else can we do? Let's add an X label and a Y label. So let's do PLT dot X label, right? And the X label should be test sample number, maybe, right? Or index or whatever you want to call it. So if we run this one now, there it is, test sample number. You can see it's got that. Then let's add the Y label. So I'm going to say PLT dot Y label. And we're going to say here the rating, basically, output rating. Let's just say rating. Okay. And you can see it's got it there. I think it's spelled correctly. All right. The legend is for that label that we added. So we can do plt.legend as well. And it just makes it more presentable. People would want to know which one is which. Okay, so And it's there, right there in the lower left-hand corner. It says real data is red, blue data is, or blue, yeah, is predicted. All right. If you want to save it, you could probably do, just for completion, let's do plt dot save fig. Save fig. And then you give it a name. So we're gonna say that this is yeah, output. No, let's say pred versus real plot or something. Okay, and then you can specify, as I said, the DPI. DPI is really important because when you want to publish something, it's got to have a specific DPI, dots per sec per inch, I think it's called. So 300 should do it. And then now you have a high quality image that you can use. So if we run this one, oh yeah, that should be probably in double quotes. Variable. Okay, so it's doing something. It finished performing. Now, if we go to our Jupyter Notebook over here, you can see we probably, yeah, we added the PNG file, and that you can use for your own, publications. Got it? All right, any questions, guys? All right, so I'm gonna go ahead and save this one. Make sure I don't lose it, but that's how you generate that figure. So you guys can use, so now you have several tools, right, to measure the performance of your model. You will look at the loss function. So the loss function in the training set, if it continued to go down to 0.001, it would be a good indication that the model is doing well. But because it keeps going back from 0.4 to 0.71 to 0.5, it's kind of like stuck there. And so how do you solve for that, right? So that's the problem. So I recommend that as you do the homework, look at this one. Also look at the data itself. Look at the R-square, which is, this is actually, the R-square is the most important probably. So you should go by that really first. And then you can look at the graph, which will give you an indication of, what's going on in your model. Obviously, if you see it all blue, you should feel pretty happy because you've achieved a pretty good model. Any questions? Does that make sense? Nope. All right, so the next thing we're gonna do before we start building other architectures is we're going to normalize the data or scale the data, right? So we're gonna go back up. So I've given you at this point pretty much all the metrics that you can use for this to look at performance. And now that we know how to look at performance, we're gonna focus on how to improve performance, right? And the first thing I would always say when you have data like this, I would look at the data. Once again, I'll repeat, I would go up here, take a look at the data and see, okay, these are decimals, these are like 7 or 6, these are like 111, 110, scale it. That's pretty much the first thing I would tell you to do. So either normalize it or standardize it. So today we're going to standardize it, okay? So standardization is basically just an equation that you apply. So I'm going to switch over to the whiteboard here and show you what I mean. So we're going to write out the equation. So I'm going to share the whiteboard. Okay. It's really a simple equation. You take your X values. So this is X, right? Now you think of it as for one sample or all samples, right? You guys know that we treat everything as matrices and we perform operations on matrices. So you can do this as the X and call this one X, scaled, for instance, right? And that's going to be equal to X. And it's going to be basically, if we are going to perform this calculation, just want to make sure I do this right? So it's going to be minus the mean of X. So let's say X mean. X mean. So the mean is the mean, right? The average. Okay. And then that's going to be divided by the deviations, the standard deviation. So it's going to be x. So the all of x, right, in relation to x, let's call it deviations. And that's it. So that's what we need to do. So for a matrix of x, right? So let's think of a matrix. Now you only do this on the train set. You don't do it on the test set because they both come from the same population. And you wouldn't have access to the test set anyway, right? In theory. So really you perform this on the train set and you apply it to both the train and the test set. Make sense? What you're doing is, if you remember, the train set has roughly 4,000 samples, right? And it's got 11 of these, correct? So what you end up doing is you average across this direction. Which dimension is that? That's dimension 0, right? In a tensor or a NumPy. And the mean of this whole thing would be 1 by 11. Just like that. So it's the average of this column, the average of this column, and so on. Got it? Does this make sense, guys? And then you do the exact same thing for the standard deviation, and that's also going to be a 1 by 11. Make sense? Questions? I think we did something very similar with images, right? Do you guys remember when we were normalizing some images and during the basics phase? Yeah. Any questions? So we want to average all y separately, right? Because some were acidity, some were like sulfate, some were like alcohol content or something like that. One variable has nothing to do with the other one. They're in fact known as independent variables, and the only dependent variable is the rating. Okay, so we perform the operations such as this. This is the formula for standardization. Okay, remember, not normalization. Normalization is another slightly different but similar at the same time formula. We might explore that later, or you on your own try it out. Okay, it's very similar. At the end of the day, we want to get the best performance possible. Okay, so we've got about 16 minutes. So I think in those 16 minutes, we can write in the code for this, and then we'll just leave it running and take the 10-minute break. Okay, and then we will come back. Any questions before I do this part? All right, so let's go ahead then. I'm going to stop sharing this. Okay, now go back to sharing the screen. Share the screen. We're going to get back to our code in the Jupyter notebook over here. And I think I had a section for this. Yep. So let's just add it in here. So what we need is, first of all, for the given data, I need the means and the deviations, right? So I'm going to do that here. I'm just going to say that I want that vector x means. And that's going to be, because that's easy to calculate. Now, remember, our data is already a torch tensor, right? It's over here, x train tr. Remember, as I said, both x test tr and x train tr come from the same data set. Because you would never have access to the test set, you only use x train tr to calculate the means. So then we go over here, and this tensor has a property called mean. And then we just tell it the dimension, which is 0, across all the rows, basically, right? And then we say keep dimension equal true. All right, we repeat that for the standard deviation. So let's call that x deviations. Okay, so we're going to say x underscore train tr dot standard deviation. We're going to specify the dimensionality, which is 0, and we're going to say keep dim equal true. Now here I'm going to do some additional thing. I'm going to add the epsilon. Remember that epsilon value, which was like 0.001? Why do I do that? if you remember, we were dividing by this, right? So what if this is a very tiny number? It almost becomes a 0, correct? And you don't want to divide by 0. So by adding that epsilon is like a making sure that you don't end up with a nan, not a number or something like that. That's going to error out. Okay. Any questions? All right. So we've calculated the two vectors. You probably want to look at them. So let's go ahead and run it. Let's run this one. Run it. Okay. So we've calculated them. Let's add a few cells in here. And now let's print it out. So we can print x means. And if you notice, it's got 11 values in there. So it's a vector of 1 by 11. And that's basically the means of all your dependent variables or your columns in your data set. And then we can also do the same for x deviations. So that's going to be just like that. And it should be the same 1 by 11. And there you go. You calculated those values. And now we just need to define the equation. Now, we could normalize the data outside, right? Like right here, I could normalize the data. However, we want to think about the fact that we are going to be deploying these models, right? Remember what I said? And this is a good moment for me to remind you, if you haven't done so already, create your GitHub account. Because you will, probably next, after the exam, next lecture, we will deploy these models using something called the Onyx framework. And we want to deploy it as a website, and GitHub Pages, which is the thing in GitHub, will let us, deploy simple static websites. And so they support JavaScript, but so we'll be able to deploy this. Okay. So please create your GitHub account. But because of that, because I'm going to deploy these models on the web, I kind of, what's going to happen when you have a new test sample and you give it to that website, right? Because this is normalized, you would have to separately normalize it and then put it in. So what we're going to do is we're going to do the normalization inside the deployed model. Got it? So that will be the idea. All right, so let's go ahead and do that. So we just have to do a small modification to our model, okay? We already have the x means and the y means. So now we're going to go to the bottom section here where we defined everything. And now we're gonna assume that we can pass something to the class, the instance that we create. So we're gonna pass x means, comma, x deviations. You see that? So we're gonna pass those as parameters to our model when we instantiate it. Do you guys understand? Okay, so in theory, when we instantiate this object, right, it needs to have two variables inside the class that are expecting some inputs, right? So that's what we're going to give it. And then as we run everything, we have a model that saves that data because it saves the weights as well, obviously. And then we save it as an Onyx model and then deploy it to the web. All right, so x means and x deviations gets passed here, and that should be all we have to do. So then, of course, we do have to make a slight modification to this linregnet so that it can store that data in its model. So the way to do it is in the init function, not the super init, but the init here. After self, you're going to put in x means. You guys can see that right now. Y means, right? Oh, sorry. Not y means. X deviations. Hope I didn't make that mistake somewhere else. Yeah. Yeah, should be like x means, x deviation, sorry. And then in the object, it's very important that we are able, just like it's going to store the weights, because it's got that built, it inherits that, the parameters thing, right? From the nn.module, now we can create our own variables in here where we can just like store data. So this is going to be self.x means and self dot x deviations. You guys see that? And then we are going to basically provide x means and x deviations. Yeah, like that. All right. So that's the only change. And then, of course, here, before we actually run x into linear, what do we have to do? We have to, here, this is where we actually scale it, right? Or standardize it. So we can simply just do x equal, how would you write this? This is where we do the standardization, right? So x equals x minus, very good. X minus, x means, very good, yeah. X means, right? Just like that, and then divided, right? X deviations, very good, excellent. Yeah, that's it. You see that? So, so we are actually performing the operation inside the class, and the beauty of this is we can deploy the whole thing. All right, so that should do it. I think that does it. So x, oh, it's a class, right? So what am I doing wrong here? Self. Yeah. All right, so x equal x minus self dot x means divided by self dot x deviations. That makes x now standardized. And now we run it through the linear function because we're still just at a linear model. But the idea is that hopefully by standardizing, we can take our R-squared from 0.25 to something higher and prove to ourselves that it works, right? That's the idea. I want to prove that it works. So let's take a look at the R-square. So the R-square was 0.25, right? So now I've said that standardization is a good thing. So let's go ahead and run it. I'll run it from here. So run. Actually, let me run it from the beginning. Do restart and clear output. And go ahead and run all of it. Okay, so I'm going to start here. Save. Run. Okay, so I got correlation, coefficient, matrix there. Let's keep going. Okay, keep going. Splitting the data. Okay, calculating the x means and x deviations. There we go. Data loader. Go. Our class is now done. Training loop. Okay. Okay, that's the training loop function. Train it. Okay, no errors. So run it. Okay, so we'll wait about 400 iterations. Huh? Yeah, and then that'll be when it finishes, we'll take a 10-minute break and then we'll come back and the rest of the class will just be creating other architectures and playing with this model, right? And this will be your homework assignment, as I said, improving this performance. Any questions? Are you guys understanding what we're doing? also, since you're all running with the random seed, a different random seed, it's possible that you're gonna get different values because we're doing different splits of the train and test set. So anybody that gets, you know, an R square that's really high, let me know. Because we want to determine what's the highest possible R square that we're reaching. You know, as we try to improve this to get it as high as possible and as close to 1 as possible. Yep, so that's it's running. Where? Which part? There? Got it? Good. Guys, with just check your homework assignments. As I said, I've already graded everything. Just a few reminders, you're supposed to submit PDF reports, right? Don't submit the Jupyter notebook because I can't run that. You can attach it if you'd like. But submit a report showing and also showing screenshots that you actually got the output, right? Don't just give me code. I mean, so I need to see it's about the analysis and stuff like that. I always need to see your metrics. So if you missed that, you know, I think I replied to all of you that did just to resubmit it. I'm only doing this in the beginning, right? So don't make it a habit, please. Just know you always need to put in a PDF report in there with screenshots or like the code running, basically. Okay, so check your grade book if you have any issues, and then we can talk about it at the end of class. All right, did it finish or no? All right, yeah, it's almost done. So we're, you know, moment of truth, right? So I'm saying that standardization should give us better results, but machine learning will tell us really, right? So that's the beauty of this topic, at least, that we always know if it's doing well or not. So let's go ahead and we trained the model. So now we're going to run it on the test set. Okay. And, you know, this is, again, the moment of truth, right? R squared, this is where it's 20, huh? The same. Huh. That's not good. Okay. There's the graph. Was it 0.25 for everyone? Is it 0.25 for, it can't be 0.25 for everyone, unless I made a mistake. Guys, did you all run this? What did you get for the R square?
Mine was 0.26.
0.249?
My first was 0.22.
0.31?
First was 0.22, not 0.26.
Yeah, okay. Yeah, so it should be 0.25. Okay. I mean, the data is standardized, I think. Let me double check. Yeah, that should be it. So, okay. The problem with this is it takes so long to train, right? It seems like, let's take a look at this. So let's not run it for 400 iterations because that's a lot. It seems to be at, 180, you think? Yeah, right, that's. Yeah, so 200, let's say 200 iterations. Let's run it again. So I need to go all the way to the top. Change it to 200. Okay, run it again. Now, somebody got a 0.31. 31. I don't know, like I said, it's not doing so great yet, so we got to find a way to improve results. This is correct, I think. It's going again. So run, everyone should be running this, okay? And
0.29.
0.29. Yeah. I believe if you give it more epics, it might be a good thing.
The first time I did 1,000.
Mm-hmm.
Epics, and then I got 0.22.
Okay. So, okay. Things that you need to do, right? So obviously I'm going to give you some architectures. Other ones. This is a linear model. We're going to try non-linear models. That's one thing. That's what neural networks, where they would come in. Other things you can do are play with the learning rate. See how I gave you this list of learning rates? Play with them, try different ones. The batch size usually doesn't do much, but you can play with that. Doesn't have to be very big, 16, 32, 64, something like that. Give it more epics, 10,000 epics overnight. Yeah, try that. We standardize it, so we are doing what we're supposed to do, and this looks right. This looks right. These values look right to me. And then I'm pretty sure we applied this correctly. I'm looking at it, but you can double check that this is, correct, right? And yeah, those are the things that you do. So change the architecture, play with the learning rates. Try it now with this, and then, like I said, after the homework assignment, we're going to try XGBoost and we're going to try Weka, which are two easy toolkits, and we just want to see what the best value is, okay? But I'm kind of leaving it for you guys to play with, and maybe some of you can, have fun with the homework, basically, okay? So I think it finished. 0.30 is the loss, right? So let's take a look. So what's my R square now? 0.29, so you can see it changed a little bit. Now, I am changing the data set. Do you guys remember that, right? So every time I split the data, if I ran that line of code, it's a different train set and test set. So, and that's why you want to run this multiple times. That's why we're all kind of running it, because at the end, we all are stuck at 33 or whoever got the highest. Is this clear, guys? Have you guys been running it? Has anyone reached higher than 33? Nope. All right, so it's 6:26. We're going to take a 10-minute break until 6:36, and then we're going to come back and take a look at architectures, okay? Which is the other thing that we're going to throw at it, and we'll talk a little bit about how that works. So I'm going to stop the video.